That's right. We went through all that just to talk about bonds. So now that we've defined a valence electron, let's come back and circle back to the octet rule. The octet rule is the tendency for atoms to share or transfer electrons in order to obtain a stable configuration of 8 valence electrons. The goal of every main group element is to get 8 valence electrons, and they'll do whatever it takes to get 8 valence electrons. They'll transfer electrons from one another, or they'll share electrons in order to get 8. So in order to get 8 electrons, atoms can do 3 things. They can lose electrons to get 8. They can gain electrons to get to 8, or they can share electrons to get to 8. Any of those are acceptable ways to obey the octet rule. All right, let's start with perhaps the hardest to wrap our head around first, and that's elements that obey the octet rule by losing valence electrons. That's right. They lose valence electrons in order to gain 8 valence electrons. The elements that do this are going to be metals, and those are going to be metals basically from group 1A, 2A, and 3A. How can they lose electrons and wind up having 8? Let's take a look. Let's drag our periodic table into this. All right, let me rearrange things real quickly here. How can an element lose electrons and obey the octet rule? Let's start by looking at magnesium. Here's magnesium. Magnesium's in group 2A, which means magnesium in its neutral form has 2 valence electrons. In order to obey the octet rule, it somehow has to get to 8. How it likes to obey the octet rule is it likes to lose its 2 valence electrons and obtain a charge of 2+. Well, how does that help it obey the octet rule? Well, let's start with an observation that magnesium actually has 12 total electrons, right? It has an atomic number of 12. So magnesium actually has 12 electrons total. Two of which are valence electrons. Remember, elements have more than one energy level as a general rule. So we've got magnesium's nucleus. Whoops, we've got magnesium's nucleus. Stop that. Come on, cooperate. We've got magnesium's nucleus, and we actually have 3 energy levels in magnesium. The outermost of which is the valence shell, and what it does is it has 2 electrons in that valence shell, 2 electrons in its first valence shell, and 8 electrons in that second valence shell. So what magnesium chooses to do is magnesium with 12 electrons and 10 protons chooses to lose 2 electrons. And the 2 electrons it's going to lose to obey the octet rule are going to be these valence electrons right here. It's 2 valence electrons. And they're going to go bye, bye, bye. And when they leave, look what happens to the electron arrangement of magnesium. When it leaves, that means that magnesium still has the 2 electrons in the inner, and it still has 8 electrons in its second energy level, but its second energy level is now its highest energy level. Why? Because it emptied out that first one. So in order to obey the octet rule and have 8 valence electrons, in other words, 8 electrons in its outermost energy level, it redefined what its outermost energy level was. In other words, elements in group 1A, 2A, and 3A redefine what their valence shell is. Elements that lose electrons to obey the octet rule do so by redefining what their valence shell is. A lot like Kirk did in order to pass the Kobayashi-Maru.
Sir, may I ask you a question?
What's on your mind, Lieutenant?
The Kobayashi-Maru, sir.
Are you asking me if we're playing out that scenario now?
On the test, sir. Will you tell me what you did? I would really like to know.
Lieutenant, you are looking at the only Starfleet cadet who ever beat the no-win scenario.
How?
I reprogrammed the simulation so it was possible to rescue the ship.
What?
He cheated.
I changed the conditions of the test. Got a commendation for original thinking. I don't like to lose.
Then you never faced that situation. Faced death.
I don't believe in the no-win scenario. Kirk to Spock. It's 2 hours. Are you ready?
Right on schedule, Admiral. Just give us your coordinates and we'll beam you aboard.
All right. I don't like to lose.
Sodium is going to do something very, very similar to magnesium. Now, sodium's in group 1A, is in group 1A of the periodic table, and I think we've looked at sodium enough now that you're familiar with sodium being in group 1A. If we drew a picture of our atom of sodium, sodium, the neutral atom of sodium, has 11 total electrons. And because it's in group A, of those total, 1 is a valence electron. And if we were to draw our picture of the sodium atom again, sodium, the neutral atom of sodium, has 3 energy levels with 2 electrons in that first energy level, 8 electrons in that second energy level. I said 2 in the first, 8 in the second, and then just 1 electron sitting there by itself in the third energy level. It wants to have 8. In whatever that outermost energy level is, sodium wants to have 8. Well, we now know the solution for sodium. We now know that sodium can achieve the goal of having 8 electrons in its outermost energy level by losing that 1 electron that's causing it to have to create a whole new energy level just to house that 1 electron. So sodium loses that 1 electron. Where does that 1 electron go? We don't care. Not our problem. As long as it goes. It's Marvin K. Mooney, right? Doesn't matter where it goes, just please go now. When sodium loses that electron, 2 things happen. First, it now obeys the octet rule because its outermost energy level that's occupied is now its second energy level and has 8s. 8 electrons in it, so it's obeying the octet rule. Because it redefined what its outermost energy level was and redefined I distracted myself. So it now obeys the octet rule, but it's also unbalanced its protons and electrons. Our neutral atom of sodium over here has 11 protons and 11 electrons. If it loses an electron, it's sodium, right? And we can't change the number of protons, or else we'd be changing the elements. And in chemistry, you're not allowed to change elements. Since it lost an electron, it now only has 10 electrons. So that means my sodium has 11 protons, each with a positive charge, and 10 electrons with a negative charge. So it has a net charge of +1. In chemistry, we write charges as superscripts on the upper right-hand side. Because our sodium now has a charge, our sodium can now be referred to as an ion. An ion is a charged chemical species. And the charge always results from the molecule or atom having an unequal number of electrons and protons. So the only way an ion can develop in chemistry is if the number of electrons is not equal to the number of protons. Now, everybody in group 1A, and by everybody in group 1A, I'm talking about all of these elements, because they're in group 1A, all of them have one valence electron. The easiest way for all of these elements to obey the octet rule is to lose that one valence electron, so that they've redefined what their valence shell is. So all the elements in group 1A that I have circled there, all of them will obey the octet rule. By losing one electron. That means that all the elements in group 1A, and why am I going Roman numeral all of a sudden? No idea. All the elements in group 1A will form +1 ions to obey the octet rule. Which brings up another new term, as if we haven't thrown enough new terms out here. Not only will all the elements in group 1A will form +1 cations, and I use the term I was trying to get to. Cations are the term for positive ions. Cations are positive ions, and the way you can remember it is that you can't form cations, you can't write the word cations without a plus sign, right? Cations, positive ions. All the elements in group 1A are going to obey that octet rule by forming the +1 ion. Matter of fact, remember all those explosions we saw in our lecture over group 1A elements? All of those explosions are the result of the elements in group 1A forcing their electron on other elements. They are desperate to get rid of that electron. They'll do whatever it takes to get rid of that one electron so they can obey the octet rule and form a +1 cation. Elements in group 2A do similar things. Let's take a look at magnesium. Magnesium is located right here in group 2A, meaning it has 2 valence electrons, because group number equals the number of valence electrons. Magnesium is atomic number 12, so that means it has 12 protons and 12 electrons in its neutral form. If we were to draw out the location of those electrons, because magnesium is in group 3A, well, let's see, let's get our nucleus drawn here first. Our 12 protons there. We can say the same thing for elements in group 6A. Well, they don't always form ion. Talking over myself there, forgive me. Because magnesium's in group 3A, it's going to have 3 energy levels. And in those 3 energy levels, the electrons are going to be distributed as follows. 2 electrons in the first energy level, 8 electrons in the second energy level, and it's in group 2A, so you'd expect it to have 2 electrons in that outermost energy level. So in its valence shell, because the valence shell is always the outermost energy level, so in the valence shell, magnesium has 2 valence electrons. Now remember, its goal is to get a stable octet. So just like Kirk changing the rules for the Kobayashi-Maru, magnesium's going to change the test as well. It's still going to get 8 electrons, but it's going to do so by redefining what its valence shell is. Magnesium is going to lose 2 electrons. What happens to those 2 electrons? Don't know, doesn't care. Magnesium just wants them gone. Marvin K. Muni, I don't care where you go, you just go now. That's what happens with the electrons in magnesium. First atom that's willing to take them, magnesium's willing to let them have it. Alright, so you've got magnesium. It's lost those 2 electrons. And in so doing, it's emptied out that third energy level, leaving it with only 2 electrons in that first energy level, but 8 electrons in that second energy level, which is now its outermost occupied energy level, or its new valence shell. So magnesium, like sodium, obeys the octet rule by redefining what its valence shell is and by losing electrons. Now magnesium's lost electrons, so it's gone from a situation where it had 12 protons and 12 electrons, so it had an equal number of positive and negative charges, to a situation over here where it has 12 protons but only 10 electrons. So it has 2 more positive charges than it does negative charges, leaving it with a net positive 2 charge. We write the symbol for magnesium with a +2 charge by writing the elemental symbol for magnesium. Then we write the magnitude of the charge and then the sign. Remember, for ions, it's the opposite of the way you do it in math class. For ions, you write the charge first, you write the magnitude first, then the charge. Now, all the elements in group 2A, your beryllium, your magnesium, come on, all the elements in group 2A, your beryllium, your magnesium, your calcium, your strontium, your barium, your radium, all of them have 2 valence electrons, so they're all going to obey the octet rule by gaining a 2 plus charge. So everything in group 2A is going to have a plus 2 charge. And we're going to see the similar thing for 2 other elements. Boron and aluminum over here in group 3A. They have 3 valence electrons, and they're going to obey the octet rule by losing those 3 valence electrons and redefining their valence shell. So they're going to form plus 3 ions as well. Group 1A elements form plus 1 ions, Group 2A elements form plus 2 ions, Group 3A elements form plus 3 ions. All lose electrons to form positive 1 ions, or cations. Everybody write down, you only live twice. You only live twice. The next to last Sean Connery Bond. All right, let's check ourselves before we wreck ourselves. What is the number of valence electrons in aluminum? So let's get our periodic chart out and look up aluminum. We see that aluminum is located right here in group 3A. Remember, group number equals the number of valence electrons. The group number with the A next to it equals your number of valence electrons. So if aluminum here is in group 3A, it must have 3 valence electrons. So that's our answer there. Then they want to know, what does aluminum require to acquire an octet of electrons? Aluminum is going to look really, really similar. Well, the quick answer is if it has 3 valence electrons, the easiest thing for it to do to get the octet rule obeyed is to empty out that outermost electron. Get rid of those three outermost electrons so that the lower energy level becomes its valence electron and it has 8. So we could do it simply from a memorization perspective. Aluminum is in group 3A, it has 3 electrons. It's much easier for it to lose 3 electrons than it is for it to gain 5. If we wanted to do a quick picture view of aluminum, aluminum has 13 protons because it's number 13. And it's in the 3rd row, so it's going to have 3 little energy levels there. The electrons are going to be distributed 2, 8, and 3. The easiest thing for aluminum to do to get a valence shell or an outermost shell with 8 is to redefine its outermost shell. So this is going to be another example of a Kirk ion formation. We redefine what our valence shell is. So it's going to lose 3 electrons. If it loses 3 electrons to obey the octet rule, what's the charge on aluminum going to be? Well, it would have 13 protons, and we lost 3 electrons, so it would only have 10 electrons, so it would have a net of 3 extra protons, so it would have a positive 3 charge. We'd write its elemental symbol by writing the elemental symbol for aluminum, writing the magnitude of the charge, and then its sign. Chemistry's easy, life is hard, yes? Especially hard if you're Timothy Dalton in the living daylights. Hey, you've got to love the only James Bond movie with a Duran Duran soundtrack. Why don't you make note on your paper of living daylights? All right, let's take a look at the formation of negative ions. In ionic compounds, nonmetals achieve an octet arrangement by gaining electrons. So what we saw in the previous parts of this lecture is we saw metals losing electrons to form positive ions, which we call cations. Now we're going to see nonmetals gain electrons to form negative ions called anions. Now, let's take a look here at our periodic chart. All right, here's our periodic table, and let's look at what we're talking about. We're talking about our nonmetals. And you'll remember our metal dividing line here. So we're looking at our nonmetals. Now, not all nonmetals are going to form anions. Matter of fact, we can narrow the amount that are going to form anions even a little bit more. Group 8A elements are unreactive, those noble gases. So they're not going to form anions. Your group 8A elements, your noble gases, we talked about them, unreactive. So we're really only talking about this limited grouping in here that I've circled in blue. To make matters even more interesting is, while we say that these nonmetals form anions, that's not the only way they can form chemical bonds. Nonmetals can also form what's known as covalent compounds. So, to put it very simply, nonmetals are like the most interesting man in the world. They don't always form ions, but when they do, they form anions. Nonmetals in group 5A, 6A, and 7A don't always form ions, but when they do, they lose electrons to form negative ions. All right, let's take a look at the elements in group 7A. The nonmetals, specifically I'm going to be looking at those guys, and to a lesser extent acetine. The elements in group 7A all have 7 valence electrons because they're in group 7A. Well, we know, based on the octet rule, that they want to have 8 electrons in their valence shell. So it's not a big leap to say, hey, they want to gain one extra electron and gain a negative charge. But let's role play it out. Let's take a look at chlorine. Chlorine is right here. It's in the third it's in the third period. 1, 2, 3. So it's going to have 3 energy levels. It's number 17, so it's going to have 17 protons in its nucleus. 1, 2, 3 energy levels. 2 electrons in the first energy level. 8 electrons in the second energy level. And then 7 electrons in the next energy level. It wants to have 8 in that outermost energy level. It wants to have 8 in this final third energy level. Well, the easiest thing for it to do is for chlorine to gain 1 electron. Where does this 1 electron come from? Who knows? Maybe it found a willing sodium ion. Maybe it found a willing sodium atom looking to make an ion. It gains an extra electron from somewhere. And when it does that, that gives it 2 electrons, 8 electrons, and 8 electrons. So it has a complete octet shell, but it throws off its balance. It starts with 17 protons and 17 electrons, but when it gains that extra electrons, it has 17 protons and 18 electrons. So it has 1 more electrons than protons, so it gains a charge of -1. To write it, we would write the elemental symbol chlorine, and in the upper left-hand corner, we would denote the charge as a superscript. All of the elements here in group 7A have 7 valence electrons, so they're all going to obey the octet rule by gaining 1 electron and developing a -1 charge. So everybody in group 7A is going to develop a -1 charge. We can say the same thing for elements in group 6A. They don't always form ions, but when they do, they're going to do it by gaining 2 electrons. For example, if we took a look at oxygen. Oxygen is in group 6A. Oxygen has 8 protons and 8 electrons. This little picture is a little bit different for us. It actually only has 2 energy levels, 2 electrons in the first, 6 electrons in the second. To obey the octet rule, oxygen is going to gain 2 electrons from somewhere, and when it does so, that means oxygen will now have 2 electrons in the first energy level, and it'll have 8, the magic number, in its valence shell, or its outermost energy level. But that upsets oxygen's balance. Oxygen, being oxygen, has to have 8 protons. But since it gained 2 electrons, it now has 10 electrons, or a net surplus charge of 2 negative. So it forms a -2 anion. All the elements in group 6A will do something similar. All the elements in group 6A, when they form ions, they're not always going to form ions, but when they do, they're going to form -2 anions. And just like with cations, we write the number, then the charge. So it'd be 2 negative as opposed to -2. And we'd write the charge as a superscript on the right-hand side. Why don't you write down the man with the golden gun? Everybody write down the man with the golden gun. Then there were two. There are two last elements we need to deal with. And those elements are in group 5A. In group 5A, well actually let's pull up group 5A. One thing I don't like about this periodic table is it doesn't have that nice little staircase step down it. If we were to draw in our staircase step, I'm going to draw it in here. Remember, most periodic tables have that staircase step that separates metals from nonmetals. If you look at group 5A, there are actually only two nonmetals in it, and that's nitrogen and phosphorus. So nitrogen and phosphorus do their own thing when it comes to forming ions in an ionic compound. Nitrogen and phosphorus have 5 valence electrons. The easiest thing for them to do to get to 8 when they form ions is to gain 3, meaning that nitrogen and phosphorus will form -3 anions. Arsenic, antimony, bismuth, the rest of these guys, they won't really do that. These arsenic, antimony, bismuth, these guys aren't really going to form negative ions, at least. We're not going to talk about those. We're just going to focus on nitrogen and phosphorus, and you should have no problem remembering that they will form -3 ions when they do form ions. Let's summarize our ions. Here's a chart that summarizes your ions. Your group 1A elements are +1. Your group 2A elements are +2. Your group 3A elements, but by 3A we talk about basically aluminum, are going to be 3+. Your group 5A elements are going to be 3-. Group 6A are going to be 2-, and group 7A are going to be -1. And those are the charges in your neighborhood. And that pretty well summarizes this lecture, except for the fact that I want you to write down GoldenEye. Everybody go ahead and write down GoldenEye.